Robots can go where man cannot. They can become our avatars in difficult, dangerous, and extreme environments.
Our haptic exoskeletons transfer the feeling of touch from a robot to a human.
In the future, this kind of civil flying robots will be everywhere.
One of the great successes for robot will soon be the exploration of extreme and dangerous environments.
Well, when you think about space, robots rule the day.
We probably will send artificial beings to other planets.
From space to natural disasters, the final frontier of human exploration is moving further ahead. Let's discover the most amazing explorer robots that Europe has to offer. Eyes that can see better, arms that can lift impossible weights, legs that can move effortlessly over rough terrain. Inhospitable and difficult environments that would normally be unreachable now become accessible thanks to a new class of robot explorers. The human body is a perfect machine. But even perfection has its limits. There are places, like space, where our bodies can't function autonomously. And there are instances like natural disasters or hazardous areas, where the danger threshold can be too high for our direct involvement. Here, we can use a different kind of machine, built by us, maybe less perfect, but vastly more efficient. Not surprisingly, the exploration of extreme environments is one of the main areas of research in robotics. The human element is not eliminated, but simply reconfigured. The robotic component can simply be a shell, as in the case of exoskeletons, wearable devices that give exceptional strength to their users. Like the body extender, an exoskeleton developed in Italy at the Percro lab of the Sant'Anna School of Advanced Studies.
Body Extender è un esempio di sistema robotico indossabile in grado di inseguire i movimenti dell'operatore e amplificarne le forze. Applicazioni possibili sono per esempio la rimozione di macerie nel caso di disastri naturali o provocati dall'uomo, finalizzate al recupero di una vittima, per esempio.
This exoskeleton makes it easy to lift up to 100 kilograms. And thanks to 22 electric motors in its joints, the freedom of movement is nearly uncompromised. But not all exoskeletons are designed for superhuman strength.
Our exoskeletons are haptic exoskeletons. They transfer the feeling of touch to human operators. So the human operator or a human user of an exoskeleton can feel what a robot does that he controls.
These remote control systems are being developed at the European Space Agency in the Netherlands. And they'll be used in future missions to explore other planets or moons.
The future of spaceflight foresees humans in orbit of planets and robots on the surface. Our systems support this mode of operation of future of spaceflight.
The goal is not to enhance the capabilities of the human body, but simply to transfer them to a robot. These exoskeletons relay our senses to a robotic avatar, which is designed to recreate the fine motor skills of our own hands.
With our technology, we can operate very sensitive equipment on Earth from space by robots, remotely executed by astronauts. We can handle springs of spaghetti without breaking them from space. Very fine, dexterous tasks.
Another type of exoskeleton is in development at the German Aerospace Center in Munich. To better convey the sensation of actually being in the remote environment, it uses a virtual reality system.
This haptic interaction device is a force feedback system composed of 2 robot arms. In the robots we have sensors that measure the interaction force between the human and the robot, which makes it really safe to operate with the robots. I can even share the workspace between the human and the robot. We have also a head-mounted display which provides a 3-dimensional view of a remote or a virtual environment. So I can feel as if I would be in this remote environment.
The exoskeleton is connected to Justin, a humanoid robotic platform that can perform different tasks both in space and here on Earth.
One application of Space Justin is repairing satellites. So if we have a broken satellite, we send Justin into space and he's going to repair that satellite. Therefore, force feedback is really essential because with the force feedback we can control the forces that are applied in space. Therefore, we can handle also very fragile electronic compartments, for example. The second application of Space Justin is on Earth. For example, if you want to repair an industrial plant where there is danger, risk for a human operator. Here we can use Space Justin to repair the industrial plant in a dangerous situation, to handle also standard industrial components.
Also in Germany, at the Research Center for Artificial Intelligence in Bremen, we find another humanoid robot designed to operate in space, called Isla. Like Justin, Isla can be teleoperated from a distance with an exoskeleton, and the focus of her design is in manipulation. Thanks to her flexible fingers and a complete array of sensors, Isla can handle tools with human-like precision and lift objects with both her arms. A robot like this could be controlled from Earth as it works in space, maybe aboard the International Space Station, like in this replica module that's been recreated in the lab. But to simulate an explorative mission on the surface of other celestial bodies, a large portion of the lunar surface has been reconstructed in Bremen.
This model of the lunar crater helped us over the last couple of years to design systems that are capable in their system design, in their mechanical design, as well as in their algorithmic control to cope with very unstructured and steep terrain that we will be facing when exploring lunar craters.
The stage is part of the iStruct project, which uses nature as an inspiration for building space robots. The goal is to make them move more naturally, so that they can have more flexibility and adaptability than traditional rovers. This one is nicknamed Charlie, and it's inspired by the chimp. Just like our close relative from the animal world, this robot can go from walking on 4 legs to standing erect. Something that comes in handy when you need to perform complex maneuvers on uneven surfaces, like a crater.
If we imagine a robot like Charlie within the space exploration scenario, the mobility of the robot can help to overcome certain obstacles. If we, for example, have to go into a crater, in the beginning the crater has a rim which we have to overcome, and there the additional degrees of freedom within the spine will help the robot to overcome this obstacle.
No man has set foot on the moon since 1972, and the costs for a new manned mission remain too high. But our natural satellite continues to fascinate us, and robots can be a great human substitute, keeping costs down, but still allowing for a great level of operational control.
The future missions for exploring the moon, for example, will be missions that are robotic-driven. They will be robotic missions to 90–95%, and only a small fraction will be human intervention. And therefore, the kind of systems that we bring into such a scenario have to be autonomous to a large degree, but they cannot be fully autonomous. So what we have created are, we call it supervised autonomous system that require only partial information exchange with a human operator, even on Earth or in the orbit, in order to fulfill the complete mission.
The European Space Agency is not gazing at the Moon, though, but at Mars. The Red Planet is a perfect example of an extreme environment in which the use of robotic systems is not just advisable, but may be inevitable. A NASA research study has revealed that over the course of a trip to Mars, a team of astronauts is likely to receive a lethal dose of radiation. And the return trip would take over a year, with overall costs ballooning up to hundreds of billions of dollars. That means that robots are currently the only feasible way to explore the planet and search for traces of microbial life. This is the goal of the ExoMars mission, a joint project of the European and Russian space agencies that's due to launch in 2016. It will include a rover, which is currently being tested in a faithful reproduction of Martian soil.
In this Martian simulated terrain, we have tried to recreate as much as possible the conditions to help us perform the research and development for planetary exploration robotics. In the sense of like recreating the Martian terrain roughness, the optical characteristics of the soil in terms of color and texture, and also the lighting conditions.
Once deployed on Mars in 2018, the rover will have to face heavy radiation and extreme variations in temperature from night to day. And will have to operate with the limited power provided by its solar panels.
Designing a robot for a planetary exploration is very challenging because it has to operate in extreme environmental conditions in terms of temperature and radiation, with very constrained resources in terms of mass that we can launch and send on the planet and power that it can harvest while on the planetary surface. Once on the planet, the goal is for the rover to cover 50 to 100 meters distance per day. Of course, you can understand that this is very slow, but since a system has to be fully autonomously running on Mars, relying on its own resources and its own intelligence, plus its own locomotion system, this provides an amount of safety, but this number also comes from the constraint of the onboard power in terms of computational power and actual electrical power that we have available to use.
The ExoMars rover has 6 wheels, just like the 3 NASA rovers that are already on the planet: Spirit, Opportunity, and Curiosity. But to avoid the same fate of Spirit, which has been stuck in a sand trap since 2009 and is no longer operational, ESA researchers are trying to go one step beyond.
One very particular characteristic of the rover is the capability to wheel walk. We have re-engineered this from the whole mechanism of the rover deployment once on the planetary surface. This wheel walking motion allows the beams of the wheels to swing while the wheels are rotated, giving then kind of a walking pattern to the whole system. We envisage that the wheel walking mode can allow the rover to get out of difficult situations, like for example if it gets stuck, because it offers a locomotion mode completely different than what brought the rover in this situation.
Robots, in their various shapes and sizes, may very well be the next logical step in space exploration, because they allow us to be ambitious but with far fewer risks and costs compared to manned missions.
Robots are very suited for space. Humans are not. It's extremely expensive to send a human astronaut up into space. It's very risky, and frankly there's not very much for us to do once we're up there. It's a lot more efficient to send a robot if we want to explore Mars or the moons of Jupiter to see if there is life there. I think that in the long run, robots will inherit the universe. Possibly with human consciousness riding along for the tour, if we perfect technologies for transferring human minds into machines. Some form of awareness of the human type might ride along with this expansion, but the human body is just radically unsuited to space colonization or space exploration.
But the exploration of space has always been a way for humanity to transcend its limits, even because of the hardships and the dangers that have always been a part of these missions. So, will robotic expeditions manage to provide the same sense of wonder and discovery?
It's an interesting observation that real discovery apparently requires a real human being there and plucking a flag into a piece of rock. It's something very, very human to feel that a place has only been taken over if there's real human presence in the place. So to that regard, it will probably feel fake. Have we been to Mars already? Well, we've put robots on Mars, but has humankind been to Mars already? Probably not, because we haven't put a human being up there. So to that regard, it shows us that an artificial being is not the same as a real being and is not considered as that. So to that regard, probably some people still want to put a human onto Mars, even if we could put a robot.
Robotics research is not only looking at the stars. Robot explorers can also be helpful here on Earth, especially in search and rescue missions, where a variety of different devices can be used to save human lives in difficult and dangerous conditions.
Search and rescue is the only field in robotics where you need to address the most challenging scenarios, both in mobility, in manipulation, and in perception. So if you're able to solve these problems in search and rescue, you can apply all this work to many, many other fields of robotics.
As we are engineers and roboticists, we build machines that can work outside. So if you consider the current landscapes in robotics, they are essentially just working in industrial plants, doing dull pick-and-place operations, but they are not able to work in a natural environment where humans can work, where we can go. And this is one of the main reasons why we are building legged systems, that they are able to actually go in these situations and work hand in hand with us.
Inspired by nature, legged robots can tackle pretty much any terrain, and they already exist in various sizes and configurations. This hectapod has been developed at the University of Delft in the Netherlands. It's shaped like an insect, and it's called Zebro.
Zebro is a search and rescue robot. It's been developed to go into scenarios where it's very difficult to locomote. Imagine, for example, a situation of an earthquake where a whole building collapses, and it's unknown the interior of this location, and you need to send a robot there to build a map to give to the firemen. Search and rescue robots nowadays mostly use tracks or wheels. We decide to follow a different approach. We use legs, and there's a number of reasons for that. Number one, with legs, you're more flexible where you interact with the ground, and this allows you to overcome more different classes of obstacles. Moreover, you do the minimum interaction possible with the terrain, which is very good in a search and rescue scenario where you don't want to destroy your environment. And third, you can use the legs to actually manipulate your environment, which you can definitely not do with tracks or wheels.
Robotic legs offer great flexibility in terms of locomotion, but they can turn out to be useful even beyond search and rescue operations.
Building legged systems has a lot of advantages. First of all, we can go outside. We can operate where currently just humans can operate, or animals can go and machines are not able to go to. This opens a lot of new applications. For example, if you think about the dangerous tasks in a search and rescue example, or in a natural disaster in general, for example, Fukushima that we had in 2011. So all these things where currently humans have to go into, operate there in a dangerous environment. In the future, we can think of robots going there and helping us and doing all these tasks for us. The other thing is more on a fundamental or on a principled way. By understanding this, we can also help us humans. If you think of an amputee that has no ankle joint anymore, instead of walking like Captain Hook did in the early ages with a wooden foot, we can now make activated joints there and increase the locomotion capabilities of this system quite drastically.
This is Starleth, a walking robot capable of moving quickly and efficiently on its 4 legs. It's been developed at the Swiss Federal Institute of Technology in Zurich. The legs are not stiff, but they include a spring system that's modelled after the muscles and tendons of mammals, to give the robot more control over its movement and the ability to absorb shocks. This larger quadruped robot is called HiQ, and it comes from the Italian Institute of Technology in Genoa. It can run at 2 meters per second and can jump up 50 centimeters from a standstill. It has been designed to recreate different walks and gaits to better adapt to different terrains. If nearly 100 kilograms of weight for a robot animal does not impress you, take a look at the mantis. It's a 6-legged, 2-ton robot insect that can reach 3 meters in height and 6 meters in length. Unlike the robots we've seen so far, this hasn't been created in a university or a research lab, but it's a pet project of a special effects and mechanical creatures professional. And even though it is designed for fun, the mantis has nevertheless attracted interest from companies that would employ it in industrial applications.
So applications for this kind of machine usually come under the categories of difficult terrain, let's say. So a couple of companies have seen this on the internet. One of them has a possible application for this underwater, where it gives more traction than wheels or tracks. And another company spotted the fact that the foot pressure on each leg is about, on this particular machine, at 2 tons, the foot pressure is about the same as a human foot, so it does very little damage to the terrain. And in their application in the rainforest, that's a very good thing.
Quadcopters are not a new invention. The first prototypes date back nearly 100 years. But recently they've had a surge in popularity, and many commercial models are now available and can be controlled via a smartphone. Their stability is exceptional and even allows them to come into contact with the explored area, like this model designed at the Swiss Federal Institute of Technology in Zurich.
This quadrocopter is designed for 2 specific applications. One is related with inspection through vision, and the other one is related with inspection through contact. For example, if we have a coal power plant, we want to inspect the boiler pipes. This is done so far with humans. They enter inside, and this takes a lot of time until they inspect the whole area. We want to automate this process, and therefore we have this robot, and it goes initially with the cameras. It inspects to find potential areas that have problems and corrosion. And if we find these potential areas, we go there and get in contact with the boiler pipes to measure their thickness. And therefore we minimize the amount of time it takes to inspect the whole power plant.
At the Delft University in the Netherlands, an entire lab is devoted to the design of micro-aerial vehicles, with the goal of making their components progressively tinier. Smaller size and weight are great for flying in tight spaces with greater energy efficiency, and have the added benefit of making the devices even more portable.
This is the smallest open source autopilot in the world. It only weighs 2 grams and is 2 by 2 centimeters. It has everything on board, all sensors to make your plane autonomous fly. We make it open source so that everybody can use it to fly their planes autonomous. We don't know yet why people will use it, but that's the reason why we make it open source, so that everybody can come up with a killer application like Facebook was for your iPhone, and we hope to see it soon for this kind of drones also.
The goal, as they say here, is to get one of these drones in every fireman's pocket. But the open source philosophy allows everyone to create new applications for the robot. This could be the key to making these devices very popular, and researchers in Delft are positive that this will happen in the coming years. Meanwhile, in the Delft lab, other fascinating aerial vehicles are being created by looking at insects.
For indoor flight we use flapping wing vehicles like this Delphi. It flops with its wings. It's inspired by nature, like insects flop its wings. And it only weighs 17 grams, so all the sensors, even the camera, which streams images to a ground station, total weight is 17 grams. It's ideal for indoor flight, for search and rescue. If a building is collapsed, you can fly this Delphi into the building and look for people that has to be rescued.
Flying robots can take inspiration not just from the morphology of insects, but also from their behavior. Swarm intelligence allows for the production of several low-cost vehicles, not very smart individually, but capable of astonishing group results through data sharing. From Earth to space, from military operations to decontamination, from search and rescue to the exploration of unfamiliar environments, robot explorers are being created to help us and support us in many different ways. But the way we use them is ultimately going to be the most crucial factor.
What will be a challenge is if we equip robots to do the quote-unquote dirty work, to arm them, and have them make autonomous decisions. These decisions will probably not be unethical because these machines are not built to be ethical. Do we really want UAVs making an autonomous decision whether to fire a rocket or not? Do we really want autonomous tanks making autonomous decisions with regard to firing their weapon? That might run out of control at some point.
And as is the case with all revolutionary technologies, is there a tangible risk that these robots will be more efficient than humans at many tasks, ultimately replacing us?
I don't think it is about robots taking our place in some cases. I think it's more about us giving and delegating to robots the things we don't want to do. And we don't want to do them because they're boring, or we don't want to do them because they are extreme or too difficult. So of course one of the key field of operations are going to be the one where it's very difficult for us to do it. Think about space, think about radioactive situations, think about all the other extreme situations where it will be too risky or dangerous or difficult for us to play.